Chapter 10, Forces and Motion. This whole chapter deals with, as the title says, forces and how forces affect motion, velocity, acceleration in particular, how we show forces on diagrams, how we measure forces, and so on. So the first section of the chapter is to do with diagrams. Whenever you do any calculations with forces, it's a good idea to draw a little diagram to show what's going on. We show forces as arrows. If you look at this diagram here, we have a particle, an object, and in this diagram we have four forces acting on it. The forces are shown as arrows, so the arrows pointing the direction of the force, and we would write on the arrow, if we know it, we'd write the value of the force measured in newtons. More of newtons in part 3. So let's say you had a force along here of 10 newtons and a force this way of 20 newtons, a vertical force that way of 5 newtons and a vertical force down here of 5 newtons. So you'd show it on a diagram like this. In this particular one, because you've got 5 newtons going vertically upwards, 5 newtons downwards, these two cancel each other out. So vertically, this particle would be in equilibrium. It would not accelerate upwards or downwards. Left and right, however, because you've got 10 newtons this way and 20 newtons that way, the resultant is 10 newtons of force pulling this way. So this particle would accelerate in that direction, and there'd be a 10 Newton force, the resultant of these two, a 10 Newton force pulling them that way. In this diagram, we've got a brick or a block on a surface. In this case, it's a rough surface. I'll explain why in a minute. It's a rough surface. So as it's sitting on the surface, obviously we've got gravity pulling it down. So we've got force due to gravity downwards. Gravity, as you'll know, acceleration due to gravity is minus 9.8 meters per second. And force due to gravity on that object we would call a weight. And let's say we had a pulling force this way, we might call it P. This force here, drawn along the base of the object, along the tabletop, along the rough tabletop, would be friction, F for friction. Now, the object does not fall through the table. The table is obviously pushing the object up, and we call that force the normal force, a normal reaction, which we're going to call R. So that would be all your forces on this diagram. If this was a smooth tabletop, there'd be no friction. There'd be no friction here at all. So if this was in equilibrium, as it is, on a rough surface, it means the pulling force and the force due to friction would have to be the same, and the normal reaction and the weight of the brick would obviously be the same as well, assuming the brick doesn't fall through the table. So if this is motionless, then all these forces cancel each other out. P and F cancel each other out, will be the same. R and W will cancel each other out and be the same. Be aware, and more of which later on, but if this is moving along the table at a constant velocity, no acceleration, a constant velocity, the forces also cancel each other out. We'll talk more about how that works later on. Okay, just to finish off, let's look at these two diagrams here. And we're going to work out the resultant force. So on this particle, we've got 30 newtons this way, 30 newtons this way. So left and right, the forces cancel each other out. Left and right, there is no acceleration, left or right. Up and down, there's 60 newtons up, 100 newtons pulling down, so the resultant is 40 newtons down. The resultant force is 40 newtons downwards. Oops, missed my units. 40 newtons downwards. There are some slightly more complicated questions that we need to look at. If this object here is in equilibrium, if this particle is in equilibrium, so it's not accelerating at all, it means all the forces have to cancel each other out. So if there's 60 newtons pulling down and 3p newtons pulling upwards, then these two have to be the same. So 3p has to be 60 newtons, and p would therefore have to be 20 newtons. It's an equilibrium, so the forces left and right have to cancel each other out. If you've got 30 newtons pulling left and P plus 2Q pulling to the right, now we know that P is 20, so P plus 2Q has to be, those two have to be the same as that. We know that P is 20, so 20 plus 2Q equals 30, so Q therefore has to be 5 newtons. Getting a good diagram before you start any of the questions is key to getting the answers right. Making sure you've got all your forces drawn on your diagrams, up, down, left, right, and later on we'll look at forces that pull at various angles. There are two ways of showing forces that are pulled at an angle, and that's forces as vectors. That's the next section.